Hello, class. So before we proceed with the next sample problem, I skipped this slide during the lecture and it's on absorption refrigeration. Basically, in absorption refrigeration, the refrigerant is dissolved in a liquid before it's compressed and it utilizes inexpensive energy source. Examples of absorption refrigeration systems would be water lithium bromide, with water as refrigerant, and lithium bromide as absorbent. Um, so this system is limited to temperatures above the freezing point of water. Another example is ammonia water system wherein ammonia is the refrigerant and water is the solvent for low temperatures. For more details, you may view Ma'am Rowi's handout uh, on absorption refrigeration. Let's proceed with the sample problem. This one is for the Linde liquefaction liquefaction process. Okay, so let's read the problem. Natural gas assumed to be pure methane is liquefied in a simple Linde process. Compression is to 60 bar and pre-cooling is at 300 Kelvin. The separator is maintained at a pressure of 1 bar and unliquefied gas at this pressure leaves the cooler at 295 Kelvin. What fraction of the gas is liquefied in the process and what is the temperature of the high pressure gas entering the throttle valve? Okay, so I placed here the process diagram for the Lind liquefaction process. Let's label, let's label the diagram and this would serve as our given. Okay, given, we have, so given compression is to 60 bars. So it means that after leaving the compressor, the pressure is 60 bars. So P2 equal to 60 bars, 60 bars. And then pre-cooling is at 300 Kelvin. So it means that after leaving the pre-cooler, the temperature is 300 Kelvin. Next is separator is maintained at a pressure of 1 bar. Separator, so if it's maintained at a pressure of 1 bar, it means that P6 equal to P7 equal to 1 bar. So, and then unliquefied gas at this pressure leaves the cooler at 295 degrees. So, unliquefied gas, that would refer to the stream leaving the separator. Uh, 1 minus Z, it's the unliquefied fraction. It leaves the cooler at 295, so that means T8 is 295 Kelvin. And then, what else? What fraction? So that's the given and then the required. What fraction of the gas is liquefied? So that is Z. And what is the temperature of the high pressure gas entering the throttle valves? So we're looking for Z and temperature of the high pressure gas entering the throttle valve T4. Um, but before we proceed with the solution, let's try to draw the uh the TS diagram. Okay, let's try. The TS diagram using methane. So this is the TS diagram of the methane. So imagine this is the saturation curve of methane. So this point is the throttle valve. I mean, this point is after the throttle valve where the separation happens. So where where the stream enters the separator. That's what I mean. Okay, so this point is uh the point X after the throttle valve, and therefore um part of the stream remains as a liquefied gas, and then part of the stream exits as a liquefied gas. Okay, so this is stream 7, this is stream 6, the liquefied portion. And the liquefied gas, um, okay, so the unliquefied gas is brought back to the original state at point 1. So this is point 1. This is the point uh where the gas enters the compressor. So what else do we know? Um, this is an isobar. Okay, this line right here, cooling P7 to P8 is an isobar as well as to P1. And so this is the cooler part or section, point 8, point 7 to 8. Okay, 8 to 1 is where the cycle goes back to the original. And then let's look at point 1. Entering the compressor, okay, uh the gas is the gas undergoes compression. Okay. So that should be a straight line. So this is an isobar right here. So imagine that's a straight line to point 2. Okay, to point 2. And then it enters the pre-cooler. Okay, enters the pre-cooler. Okay, so this is point 3. And then finally it enters 3 to 4, it enters the cooler. Okay, this is point 4. Now, so P2 is 60 bars, T3 is 300 Kelvin. Okay, and then uh throttle valve. Okay, now it enters the throttle valve. So here the process would look like this. 4, 5. So here enthalpy is constant because of the throttling process. All right. So if we make an energy balance around the cooler, throttle valve, and separator, remember from the lecture. So the energy balance around this energy balance around the cooler, throttle valve, and separator. That delta H is 0. Okay, so there's no potential kinetic. Let's assume that the holder is adiabatic, and also there's no work, so delta H is 0, but we have to consider, so in writing the enthalpies of the entering and exiting stream, so the entering are uh or the entering stream is H3 and the exiting stream is H8 and H6. Okay, we have to consider the mass fraction of those streams. So if we want to write the enthalpies, that would be Z, which is the mass fraction of the liquefied portion, Z times H6 plus 1 minus Z times H8 minus H3, okay, equal to 0. What else? So the next step is to read the or find the H of for each of H6, H8, and H3 so that we can solve for Z. Okay, so this is H3. But what are those streams? So 8 is a vapor, superheated vapor. H6 is a liquid. Right? It's assumed it's a saturated, completely saturated liquid, not subcooled. And H3, what is H3? H3 is still superheated methane. Okay, so remember, the liquefaction only happens here. Okay, so at point 6. So, and if we read the properties of methane at 60 bars and 300 Kelvin, so, or yeah, this is T3, 300 Kelvin. And we have a hint here that this line here is an isobar from 2 to 3, uh, because because this is an isobar, okay, and this is an isobar as well. So P2 equal to P3 equal to 60 bars. Okay, so let's write the solution. First, let's consider point 3, superheated methane, superheated methane. At point 3, again, the temperature is given T3, 300 Kelvin, and P3 equal to P2, 60 bars. So now we want to look at the properties of superheated methane. Okay, right now, what I have here is from Paris Chemical Engineering Handbook. Superheated methane at 300 Kelvin and 60 bar. So the um the columns are the temperature and the rows are the pressure. So from here, let's read the enthalpy. 360 bar, 1140, and the unit is kilojoules per Kelvin. From the superheated table. Okay, so let's table 2-282, superheated of Perry. This is in Perry. Anyway, if this will be asked in the exam, we will give you the necessary tables and diagrams. So H3 is 1140 kilojoules per kilogram. Okay. So we now have H3. The uh next point that we can consider is, so let's look at point 8. Point 8. Point 8 is still superheated methane. Uh Based on the diagram, and actually all of these points are superheated methane or methane as a gas. Um so point 8, what do we know about point 8? We know T8 is given, T8. But we don't know, do we know, do we know P8? How about the pressure? Right. So we need two parameters. We already have the temperature. P8 is 295 Kelvin. Kelvin. How about P8? So if we look at the TS diagram, and actually there's no this is an isobar right here. So this is one is an isobar, this one is another isobar. So we can say that P1 is equal to, I mean, yeah, P7, right? P7 is equal to P8 equal to P1. So P7 is equal to, P8 is equal to P7, which is equal to 1 bar, and that is given in the problem. Okay. Okay. So another hint is that there's no way that after the separator, there's no way to change the pressure. So whatever the pressure of the stream here is just actually the also the pressure of the stream here. And the same reasoning for this for the pre-cooler. So after the compressor, the pressure is maintained at the inlet and outlet of the pre-cooler. Okay. Next is the, so basically we're operating between two pressures, 1 bar and 60 bar, and that is that is um the compressor changes the pressure from 1 bar to 60 bar. Okay. Now we have two parameters. We can now read the properties using the superheated table. Okay. Superheated table. But at this point, you have to do some interpolation because, yeah, because there's no 295 Kelvin temperature, and then also uh it's the pressure, may pressure naman 1 bar. So by interpolation, I will not show it. Please do it at home by yourself. Teach it from table 2282. Very interpolate H8 is equal to 1188.86 kilojoules per kilogram. Okay. So we have now H8. NH3. The final the final H that we need to solve is for H6 to be able to know the mass fraction Z. So H6 is, what's the state? Saturated liquid. Saturated liquid. So at H6, the state is saturated liquid, and that is actually the part where the liquid or the fluid leaves the separator as a liquid. Okay, so that is a saturated liquid. And we can make use of the table of saturated properties of methane. Again, it's not the superheated, but rather the saturated properties of methane. But what are the conditions at H6? What are the conditions at H6? So the pressure is 1 bar. Okay. We only need one, right? We only need one. Pressure at 6 is 1 bar. So using table 2-281 Perry. So this is for saturated methane. Okay, 1 bar. We have to interpolate. Interpolate for HL. Okay. So interpolate for, so F is for the liquid. H sub F is for the liquid. H sub G is for the gas. Okay. So by interpolating at one between these two rows, let's let's also get H7. So HL, okay, by interpolate. Okay. Let's label that as HL equal to H6 for the liquid 284, or in Perry it's HF, but let's use it HL, kilojoules per kilogram, and then HV equal to H. So this one is, oh no, this should be 6. So this is 6. HV is equal to H7, so that's the fraction returning as gas or unliquefied, 796.6 kilojoules per kilogram. So now we go back to the energy balance. Z, okay, 284.73 plus 1 minus Z times 1188.86 minus 1140 equal to 0. Z is 0.05404. So this is the fraction of liquefied gas, or liquefied methane. So that is for letter A. So letter B, um, we're being asked for T4. T4 is the temperature temperature entering the throttle valve. Temperature entering the throttle valve. Okay. So how do we solve that? T4 is superheated methane, 0.4. Okay, we know the pressure, 60 bars, because this is an isobar, but we don't know the temperature. So at 0.4, superheated methane, T4 is 60 bars. Okay, and then we don't know the temperature. So if we know the temperature, then we can read from the superheated properties. I mean, if we know another property, okay, we're looking for the temperature. That's the unknown. So if we're able to know another property at this point, we can read T4 from the superheated table. And the other property that we can solve is enthalpy. Okay, let's solve for enthalpy. Let's consider the cooler. The cooler, these are the streams entering and exiting the cooler. Okay, so again, our goal is to solve for another property, which is H4. Okay. Okay, so this is um the flows entering and exiting the cooler. So if we make an energy balance around the cooler, okay, delta H is 0. And that's right in terms of enthalpy. It's simply, so the exiting streams would be H7, oops, H7, considering the mass fractions, okay, so again, this is the cooler, considering the mass fraction, so these are the exiting H7 and H3, minus the entering streams, H8 times 1 minus Z, minus H3, equals 0. Right. So rearranging, and we can write it as, oops, H4 minus H exiting, hold on. Exiting is H4. So baliktad. Exiting is H4. Yan. So this should be H4. Okay. H4. So rearranging the equation, grouping the same factor. So 1 minus Z times H8 minus H7. Oops. Equal to 0. Okay, so we have this value, H8, we have H7, kinuha natin sa kanina, di ba? H8 and then H7 from the steam table. So that part is the pure saturated vapor. So we just read off from the steam table together with H6. And we also have H3. So, and Z. So, the unknown value is just H4. So, substitute. Substitute everything and solve for H4. H4 is 768.94 kilojoules per kilogram. So now we have another property, H4, and we have P4. Can we read now from the steam table, superheated, not steam table, from the superheated table of methane? Yes, say we have two properties. So let's go to this table, 6 to 60, and find the H. Okay, that is 768. So that's between these two temperatures, between 200 and 250. Okay. By interpolation, I interpolate at enthalpy equal to 768.94. I interpolate at the pressure and um, enthalpy. So from table 2-282, vary. Interpolate at P equal to 60 and H equal to 768, you will find that the temperature is 206.6 Kelvin. Okay, so that's the solution for this problem, and let's stop the video for now. Okay.